Dear students, let us continue our study in this paper, which is environmental chemistry. And in the previous module, we studied about some analytical techniques for measuring water quality parameters, and we shall continue this study in this module also. Dear students, after studying this module, you shall be able to know about the methods for the determination of water quality parameters. You should be able to learn various analytical techniques for determination of different species in water and evaluate the total hardness and alkalinity of water. And you shall be able to analyze the different metal ions which are present in water. So, let us begin with the introduction. You know that water is linked with human welfare, and thus water quality becomes an important parameter for the entire mankind. Chemical, physical and biological characteristics of water is what is referred to as water quality. It estimates water condition as per the requirement of biotic species. The ultimate objective is for the formulation of standards which may necessitate extensive treatment prior to use is the protection of the end users, be these be humans or animals or for the agriculture use or for the industrial use. In the previous module, you have studied some of the water quality parameters, and in this present module, you shall study a few more important parameters for determining the water quality for various end uses. So, let us begin with knowing more about pH. pH is not a new term to you, but let me revise. The pH of water is defined as hydrogen ion concentration in an aqueous solution, and as you are already aware, it is expressed as you can see here, pH is the negative logarithm of hydrogen ion concentration. By definition, pH is the negative base of 10 logarithm of the hydrogen ion concentration in moles per liter. At a pH of 7, you are aware the concentration of hydrogen ions and hydroxyl ions becomes equal, and therefore it indicates neutrality. While pH less than 7 will represent an acidic solution, that is, there is a predominance of hydrogen ions, and pH greater than 7 with a maximum value of 14 will be representing a basic condition where it will be predominance of hydroxyl ions there. Because of the logarithmic scale, a change of 1 pH unit represents a 10-fold change in the hydrogen ion concentration, and this is quite a large amount. Most aquatic animals have pH preferences from 6 to 9. So, if it is less than 6 or greater than 9, it will be a dangerous zone for them. This range is usually maintained by the carbonate and bicarbonate buffering of naturally acidic precipitation. Due to carbon dioxide solubility, rain that has been affected by no other dissolved gases or ions has a theoretical pH of 5.65. The presence of acidic or alkaline compounds can lower or raise the pH of a water body respectively. The pH of water profoundly affects the chemical processes that may occur within it. If you try to know how the pH is measured, pH is measured by a pH meter using a glass electrode that produces potential linearly varying with the pH of a solution. It is a Nernstian concentration cell with potential controlled by the activities of hydrogen ion, that is, it is A of H plus activity on either side of a very thin glass membrane. The common features of a pH meter are a sensing electrode and a reference electrode connected to an electronic circuit that amplifies the voltages which is produced when the electrodes are immersed in a solution or water sample. The amplified voltage is displayed on the meter graduated in pH units, and that is how the name pH meter. Sensing and reference electrodes designed for field use are often combined in one element. A calomel, or you can say silver, silver chloride, potassium chloride reference electrode are used as standard, and they are usually located around the glass electrode. And the pH is calculated by this formula, as you can see here, that is E is equal to constant plus RT upon NF, natural log of activity of hydrogen ion concentration of sample divided by activity of hydrogen ion concentration of the standard, and this can be equated to E is equal to constant 0.058 plus pH at 20 degree centigrade. Now, talking about specific conductance. The ability of water to conduct an electric current is known as conductivity or specific conductance, and it depends upon the concentration of ions present in the solution. Conductivity is measured in millisiemens per meter, and conductivity is also temperature dependent. Thus, if the meter used for measuring conductivity is not equipped with automatic temperature correction, the temperature of the sample should be measured and recorded. Specific conductance is given by, as you can see here, by C into 1 upon A, where C is the conductance and A is the cross sectional area. Let us see how the nitrogen in different forms is there in these samples, and then how it can be estimated. First of all, let us consider ammonia. Ammonia is a component of fertilizers, sewage effluents and manure. It is naturally present in surface water and groundwater and is largely produced by deamination of organic nitrogen containing compounds and by hydrolysis of urea. Depending upon the pH, ammonia may be present as the aqueous gas, that is NH3, or as ammonium ions, that is NH4+. At usual, the natural water pH, the ammonium ion predominates. Under aerobic conditions, ammonia can be converted into nitrite ion, that is NO2 minus, and then further to nitrate ions, that is NO3 minus, through the bacterial process of nitrification. Ammonia nitrogen can be determined by any of these methods, which are spectrophotometric, Nessler's method, and this is used when ammonia nitrogen concentration is low, that is around 5 ppm, and by Titrimetric method, and this method is used when the ammonia nitrogen concentration is higher than this. Distillation of the sample is required to eliminate interfering agents present in the sample when the sample is colored and when Titric method is being used. Talking about simple distillation, if sample is colored, the distillation of colored water sample is done, and here you can see in this equation that the water sample around 500 centimeter cube is treated with dilute NaOH and then subjected to distillation, and this is collected over 200 centimeter cube of 0.1 normal sulfuric acid and then finally made into final volume of 250 centimeter cube or 250 ml. Coming to the details in the Nessler's method. In this method, which is the Nessler's method, the sample is treated with Nessler's reagent, which is K2HgIO4 in alkaline medium, whereby a yellow-brown colloidal suspension is produced. The intensity of the color produced is proportional to the concentration of ammonia in the sample. When the ammonia concentration is higher, then the reaction product tends to precipitate, while at lower concentration the absorbance is measured spectrophotometrically at 420 nanometers. As the absorbance and concentrations are linearly related, the amount of ammonia can be determined from this graphically. Chart 1 and chart 2 describe the distillation of colored sample and determination of ammonia and colorless sample respectively using this Nessler's method. So, you can see in this chart 1 that water sample when distilled with NaOH and finally it is collected over 0.1 normal sulfuric acid and made into final volume of 250 centimeter cube. For the colorless sample, you can see here the step 1 is the water sample about 100 centimeter cube is taken and treated with 10% NaOH and 10% zinc sulfate. It is then filtered and discard the first 20 centimeter cube of distillate. The step 2 is the filtrate 50 centimeter cube of is taken and 50% EDTA 1 drop is added, and then we add the 2 centimeter cube of Nessler's reagent. They are mixed well, stand for 10 minutes, and the absorbance is measured at 420 nanometers. For colorless sample, the distillate sample plus 0.1 normal NaOH plus Nessler's reagent, they are taken, they are mixed well, and the solution is put up on stand for 10 minutes and then measure the absorbance at 420 nanometers. If we talk about how to prepare the Nessler reagents, you can mix together 70 grams of potassium iodide, 160 grams of AgI2 and 160 grams of NaOH in ice cooled and dilute it to 1 liter. Alternatively, if you have to prepare lesser amount, then correspondingly decrease these concentrations in a relative manner. Now, after the Nessler's method, let us talk about the Titrimetric method. The Titrimetric method, in this what we do is, here the distillate sample is titrated with standardized dilute sulfuric acid using red methylene blue indicator until the color changes to pale lavender. After ammonia, let us now look at the nitrogen as nitrate and nitrite. Under aerobic conditions, ammonia can be converted into nitrite and then nitrate in the bacterial process of nitrification. Both of these inorganic nitrogen forms are highly soluble in water because being ionic. In absence of oxygen, nitrate can be converted to nitrogen gas through the bacterial process of denitrification. As the oxidation of nitrite to nitrate is rapid, natural waters usually have very low concentration of the nitrite, and it is the nitrate which is present in more amounts. Nitrite and nitrate can be discharged directly to water from fertilizer, sewage and manure sources. It is most essential to monitor the nitrate and nitrite concentrations regularly in the water bodies, because these may be potentially very hazardous to the health if their maximum admissible concentration, that is MAC, of 50 milligrams per liter and 0.1 milligrams per liter respectively are exceeded. Nitrate is particularly very dangerous for infants below age of 6 months and causes a child disease called as methemoglobinemia, and the permissible limit of nitrates in drinking water is 10 milligrams per liter. Nitrate and nitrite in water may be analyzed spectrophotometrically as well as titrimetrically. If we talk about the spectrophotometric method, here the nitrate and nitrite are reduced to ammonia by the Devada's alloy, which is 50% copper, 45% aluminium and 5% zinc, and this reduction is done in strongly alkaline solutions. The ammonia so obtained is then distilled into excess of acid, and it can be determined by the use of Nessler's reagent. It shows the steps involved in the estimation of the total nitrates and nitrites, and how the conversion of nitrate gets converted into ammonia. You can see in this equation, which is given 3NO3 minus plus 8Al plus 5OH minus plus water. It is going into 8AlO2 minus and production of ammonia. So, what is done here is to around, you can see this in these steps, and to 500 centimeter cube of the water sample, 50 centimeter cube of 10% NaOH is added, and the solution is then evaporated till the volume reduces to about 200 centimeter cube. To this solution, 3 grams of this Devada alloy and 30 centimeter cube of 10% NaOH are added in succession. The flask is immediately connected to a vertical condenser whose outlet dips into a receiver which further contains 200 centimeter cube of 0.2 normal sulfuric acid. The mixture is distilled at 50 to 80 degrees centigrade for 1 hour, after which the receiver is disconnected and the volume of the solution in the receiver is made up to 250 centimeter cube. An aliquot of 5 to 10 centimeter cube is taken in a 50 centimeter cube volumetric flask and the pH adjusted to 4.5. Further, 2 centimeter cube of Nessler's reagent is added and the absorbance is measured at 420 nanometers as we have done earlier for the ammonia estimation. So, this method is valid for nitrate concentration greater than 0.5 ppm but less than 5 ppm. So, for concentrations greater than 5 ppm, Titrimetric method will be used, and in this Titrimetric method the distillate can be directly back titrated with the standard alkali which is 0.2 normal NaOH using methyl red as indicator. In the nitrite estimation, the estimation of nitrite is based on a diazotization reaction in which a reddish purple dye is produced by N1-naphthyl ethylene diamine dihydrochloride at a pH of about 2.0 to 2.5. And this scheme you can see here, it shows the reactions which are involved in the formation of dye and its estimation. So, you can see here the water sample around 40 centimeter cube at pH 7, it is treated with sulfanilamide solution made of 50 grams in 500 centimeter cube of 1.2 normal HCl, and these are shaken together and allowed to stand for 10 minutes. You get this sample A, and then sample B is prepared by dissolving 0.3 grams of N1-naphthyl ethylene diamine dihydrochloride in 200 centimeter cube of warm water, mixed, then cooled, filtered and diluted to 250 centimeter cube with glacial acetic acid. Subsequently, these sample A and sample B are mixed. We take 2 centimeter cube of sample B and this is further diluted to 50 centimeter cube, and if there is a formation of purple color dye, it will indicate this. Intensity of this purple color dye is directly proportional to the nitrite concentration, and this is what is measured at 543 nanometers. So, you can see here these are the reactions given. So, first there is formation of this diazonium bound and then this coupling is happening to give this dye. So, you can see this is the diazotization reaction for the estimation of nitrites. Now, after nitrogen, let us talk about the free or the residual chlorine. Chlorine is known to kill the disease forming microorganisms found in water, and hence chlorination of water is a measure to protect public health. This generally results in an excess of chlorine which is called as residual chlorine, that is the amount of chlorine present after the demand has been satisfied, and this can be determined by the chlorine residual test. When it is added to the water sample, some of the chlorine reacts with organic materials and metals and is unavailable for disinfection. This is called chlorine demand of water. A measure of chlorine demand may be required in order to estimate the quantity of chlorine necessary to add to a given volume of water. Chlorine demand may be defined as quantity of chlorine required to produce a residual chlorine content between a trace and 0.1 ppm after 10-minute contact. The measurement of chlorine demand is helpful as it enables in estimating the quantity of chlorine necessary to add to a given volume of water. It is not at any sample you can add any amount of chlorine or the same amount of chlorine. So, this estimation is important and then only the chlorine should be added. The free chlorine reacts instantly with NN-diethyl phenylene diamine, that is DPD indicator, to form a red color, and this color is discharged on addition of the ammonium ferrous sulfate that is ammonium iron 2 sulfate solution. In drinking water, presence of chloride is relatively harmless if the amount is below 250 ppm. The chlorine content of wastewater is higher than that of the raw water. It is estimated by Argentometric method with silver nitrate solution using potassium chromate as an indicator. In this method, 100 centimeter cube or 100 ml of water sample is taken and its pH is adjusted between 7 to 10 with sulfuric acid or NaOH, and 1 centimeter cube of 5% potassium chromate indicator is added. The sample is treated with 0.0282 normal silver nitrate solution until a pink color is obtained. Silver nitrate reacts with the chloride in slightly alkaline condition and this gets precipitated at AgCl, and this you can see as it is shown in these equation. You have AgNO3 plus NaCl giving AgCl plus NaNO3, and potassium chromate also reacts with silver nitrate and you get AgCrO4 plus KNO3. To eliminate interfering agents that which can be sulfide, sulfate and thiosulfate, 5 centimeter cube of 30% H2O2 may be added prior to titration. So, this is how then it is done. Water sample you take 100 centimeter cube, add H2SO4 or NaOH to maintain the pH between 7 to 10 and then add 5% K2SCrO4 1 centimeter cube. Do the titration in the presence of 0.0282 normal AgNO3 and there will be formation of pink color. Now, after the nitrogen and chlorine, let us talk about the total hardness and alkalinity of water. Water collects impurities from various sources like soil, rock, sewage, industrial waste and by decomposition of plants and animals, etc. The water thus becomes hard and may not be suitable for various domestic and industrial purposes. Water is classified as hard or soft, you are already aware, depending upon its behavior towards soap solution. Hardness of water is defined as a soap consuming capacity of a water sample, and hardness in water will prevent the lathering of the soap. Soap is made up of sodium or potassium salt of higher fatty acids like oleic, palmitic, stearic, and these salts are soluble in water. Hardness in water is due to the existence of some salts of calcium, magnesium and other heavy metals dissolved in it. So, when soap is used in hard water, the corresponding calcium or magnesium salts of these higher fatty acids are produced, which are insoluble in water and form scum type of material. When soap is used in soft water, gets dissolved and very readily it will be forming leather. A sample of hot water when treated with soap does not give leather because it will result into a white scum or precipitate. We can talk about two types of hardness, one is temporary and another is permanent. Temporary hardness is due to the presence of soluble bicarbonates of calcium and magnesium, and they can be removed by boiling as the soluble bicarbonates get converted into insoluble carbonates. It is also called as carbonate hardness. But when we talk about permanent hardness is because of the presence of chlorides and sulfates of calcium, magnesium, iron and other heavy metals. It cannot be removed by boiling or adding slaked lime because these methods do not precipitate out the calcium and magnesium salts. Carbonate hardness, that is the temporary hardness, and the non-carbonate hardness, which is the permanent hardness, together will constitute the total hardness of the water. Hardness is generally expressed in terms of equivalent of calcium carbonate to make calculations in water analysis easier. It is most convenient to express the hardness caused by different salts in terms of equivalent hardness of a single salt. The choice of calcium carbonate is there because of its molecular weight 100, equivalent weight 50, and moreover it is the most insoluble salt that can be precipitated in water treatment. Hence, all the impurities that result into hardness are first changed in terms of their respective weights equivalent to calcium carbonate. The equivalent weight of a substance, you are already aware, is its atomic or molecular weight divided by its valency or simply the ionic charge for these cases. For calculation of hardness and alkalinity, the equivalent weight of calcium carbonate is considered, which is 50 grams per equivalent or 50 milligrams per milli equivalent. For calcium ion itself, the equivalent weight is 40 divided by 2, that is 20 milligrams per milli equivalent. And if we talk about magnesium ion, the equivalent weight will be obviously 24 divided by 2, that is 12 milligrams per milli equivalent. In calculating the hardness of water sample, the concentration of every cation is converted in terms of milligrams per liter as calcium carbonate using this particular formula, as you can see here, that is milligrams per liter of M2 plus as CaCO3, where it will be equivalent to concentration of M2 plus ion multiplied by 50 milligrams of CaCO3 per milli equivalent, and this divided by equivalent weight of the M2 plus ion in milligrams per milli equivalent. Let us consider an example to understand this. For example, you take a sample of water having 50 milligrams per liter of calcium ions and 10 milligrams per liter of magnesium ions. And then if you have to express the total hardness as calcium carbonate, let us try to understand how it can be done. What you will do is take the concentration of calcium ions, here it is given 50 milligrams per liter. So, divide it by its equivalent weight, which is 20 milligrams per milli equivalent, and you get 2.5 milli equivalents per liter. Now, using the formula that we have discussed, milligrams per liter as calcium carbonate will be then calculated as 2.5, which is this value, multiplied by 50, that is you get 125 milligrams per liter. Similarly, the concentration of magnesium ions, it will be 10 divided by 12, that is 0.833 milli equivalents per liter, and then this will be multiplied by 50, you get 41.65 milligrams per liter as CaCO3 ions. So, the total hardness in this sample will be 125 plus 41.65, that is 166.65 milligrams per liter as calcium carbonate. The hardness of water does not show pollution parameter, but it gives the water quality. Water hardness is expressed in terms of calcium carbonate and is determined by also the complexometric titrations. During the titration with EDTA, Ca2 plus ion first reacts and forms a relatively stable complex, followed by magnesium ion to give a metal EDTA complex, releasing the free indicator in blue color. The Eriochrome black tea is used as indicator and the color changes from wine red to blue at the end point, and this gives the amount of calcium as well as the magnesium ions. The titration is carried out at pH 10 by adding ammonia ammonium chloride buffer. And as you can see here, this is depicted that calcium or magnesium in the hard water, you first do the titration with EBT blue in the pH 9 to 10, where you get wine red color for this complex, and then with EDTA it will be further rendered colorless. Calcium ion is estimated selectively at very high pH at highly alkaline medium, that is pH 12 to 13, and Mg2 plus gets precipitated as magnesium hydroxide in the presence of chalcone indicator. The change in color is then from pink to blue. So, now we move to alkalinity. Hardness is commonly confused with the term alkalinity. Alkalinity expresses the amount of acid, that is hydrogen ion, which water can absorb as buffer before achieving a designated pH. Alkalinity of a sample of water is due to the presence of hydroxyl ions, HCO3 minus ions and carbonate ions, or the mixture of two ions present in them. The possibility of OH minus and HCO3 minus together is not possible, since they will combine to form further CO3 2 minus, that is the carbonate ion. The alkalinity due to different ions can be estimated separately by titration against standard acid solution using selective indicators such as phenolphthalein and methyl orange. So, you can see all these equations, that is how these ions will be reacting with H plus and giving you corresponding. So, alkalinity will be then the concentration of combination of all these ions, that is HCO3 minus plus CO3 2 minus and OH minus concentration, and this total minus the H plus ion concentration will be the alkalinity of that particular sample. The neutralization reaction up to phenolphthalein endpoint shows the completion of the reactions 1 and 2 only. Thus, the amount of acid used is equal to complete neutralization of OH minus plus half neutralization of CO3 2 minus. The titration of water sample using methyl orange indicator gives the completion point of the reactions 1, 2 and 3, as you can see here. The further amount of acid added after the phenolphthalein endpoint corresponds to 1/2 of the normal carbonate and all the bicarbonates, and the total amount of acid used gives the total alkalinity because all ions present in water sample. The alkalinity is then expressed in terms of equivalents or in milligrams per liter as CaCO3. After the hardness and alkalinity, let us move to metals. The presence of metals in water is a subject of serious concern because of the toxic nature of many metals. Some metals are good, but then many are harmful as times. Metals can neither be degraded nor be metabolized. And these are examples of ultimate persistence. Some metals are essential, others may negatively affect water consumers, wastewater treatment systems and the receiving waters. And some metals may be either beneficial or toxic depending upon their concentration. Metals enter the living organisms either as inorganic salts or as organometallic derivatives, and amongst the heavy metals, especially the mercury, lead and cadmium are the ones that have most severely affected our environment, and their permissible limits you can notice it is 0.001 for mercury, 0.05 for lead and 0.01 ppm for cadmium respectively. And if it is higher than this, it is really dangerous to the human lives, to the animals and aquatic life and so on. And if we consider these one by one, mercury is discharged into water bodies by both natural as well as man-made sources. Organic mercury compounds have been found to be most toxic, and mercury is estimated by spectrophotometric and flame atomic absorption method. In the spectrophotometric method, it is based on reaction of Hg2 plus ions with dithiazone in acidic medium, where we take one normal sulfuric acid as the acid. The orange complex formed by reaction is then extracted into CCl4 and the absorbance is measured at 490 nanometers. The sensitivity kept as 2 to 10 micrograms, and in the flameless atomic absorption method, the steps used in the techniques are: the sample is first digested with sulfuric acid or the nitric acid followed by oxidation with a mixture of H2O2 and KMnO4. Subsequently, the NaCl NH2OH mixture is added to destroy the excess of oxidizing agents, and the solution is further treated with SnCl2 to reduce the mercuric ion into elemental mercury. As you can see in this equation, Sn plus 2 reacting with Hg plus 2, we have the formation of Sn plus 4 and mercury. The elemental mercury so produced is then volatilized and directed to an atomic absorption spectrophotometer. The absorbance is then measured at 253.7 nanometers, and the intensity of the absorption is directly proportional to the concentration of mercury. So, that is how the mercury estimation can be done. Coming to lead, the most common source of lead is the weathering of rocks, industrial, mining, smelter discharges and so on. Natural water generally contains up to 200 ppb of lead. Lead is dangerous and is a serious cumulative body poison. Several methods have been reported for analyzing lead. The spectrophotometric method is the most commonly used out of these. Lead can be measured by directly aspirating the sample into an air acetylene flame and measuring the absorbance at 283.3 nanometers. For the lower concentration of lead, complexation is done, wherein the sample is treated with ammonium pyrrolidine dithiocarbamate and extracted into methyl isobutyl ketone. Aspiration of the methyl isobutyl ketone complex extract into the flame of an AAS is done, and that is how the estimation is done. Coming to arsenic. Arsenic is a metalloid and it exists in two oxidation states, that is 3 and 5. The lower valent compounds of arsenic are more toxic. Acute arsenic poisoning can arise from the ingestion of as little as 100 milligrams of it. Natural phenomena like weathering and volcanism as well as anthropogenic sources contribute to the arsenic compounds in the environment. And if we talk about their determination or the estimation, then we have the Gudget method. In this method, the arsenic is first reduced to AsH3, which is called as arsine, by a solution of zinc in acetic acid, and this is done in a Gudget generator, and hence its name. The AsH3 so formed is then passed into through a scrubber containing glass wool impregnated with lead acetate solution, and then passed through an absorber containing silver diethyl dithiocarbamate dissolved in pyridine. A soluble red complex is formed by reaction of arsenic with silver salt, and the absorbance of this complex is measured at 535 nanometers. This method is also called as silver diethyl dithiocarbamate method, and the sensitivity of this method is quite high and can accurately measure the concentration ranges from 0.002 to 0.1 ppm. In atomic absorption spectroscopic method, the AsH3 so formed is directly aspirated into argon hydrogen flame and measured at 193.7 nanometers. By this method, the arsenic can be estimated even below 2.4 ppb. Coming to cadmium. Cadmium is again very toxic and poisonous and may cause adverse changes in the arteries of human kidneys. The source of cadmium in water body is mainly industrial waste from plastic and ceramic industries. On reaction with dithiazone, Cd plus 2, that is the cadmium ion, forms a pinkish red colored complex which can be extracted with chloroform and then measured at 518 nanometer by spectrophotometer. For atomic spectrophotometric method, the sample is directly fed into air acetylene flame and the absorption is measured at 229 nanometers. Coming to chromium, Hexavalent chromium reacts with S-diphenyl carbazide in acidic medium to form red violet colored solution, the absorbance of which can be measured at 540 nanometers. AAS method is similar to cadmium except that the absorption is in this case measured at 358 nanometers. So, dear students, let us now summarize what we have learnt in this module. We have studied that acidity and alkalinity are important parameters of water quality standard and measure the quantitative capacity to react with strong base and buffering capacity of a water body respectively. We also studied that hardness is often used to measure the quality of water supplies. The hardness of a water refers to the amount of calcium and magnesium salts in case of temporary hardness, mostly in association with bicarbonate and carbonate, and with sulfates, chlorides and other anions of mineral acid in case of permanent hardness. We also studied that nitrogen can occur in the form of ammonia, nitrite and nitrate in water bodies and how it can be estimated by either spectrophotometric methods or titrimetric methods. We also studied that chlorine is used to protect the public health by killing microorganisms found in water which cause disease, but the chlorine residual test is used to measure the total amount of chlorine present as a residual, that is the amount of chlorine present after the demand has been satisfied. We also studied the presence of metals and metalloids in water bodies. They are subject to serious concern because they are very toxic even at very low concentration. And we studied that how atomic absorption spectroscopy is the most common used technique for estimation of metals in water sample, and it consists of a light source which emits light of a particular wavelength, an atomizer, burner unit for introduction of a sample into the flame, a monochromator or a filter to isolate the characteristic wavelength, and finally a detector and a recorder.